Greetings, everyone. Welcome to the Roll Your Own Crypto panel, where we have a bunch of cryptographers or people that work on signature libraries, and they're kind of unsung heroes when things go right. And if things go wrong, they end up like Sony, completely pwned. So I'd like to first get started in what is a signature, how does it work, are we using DocuSign here in Bitcoin Core? What's going on? How do signatures work, Jonas? What are the functions? What's needed?
Mm-hmm. OK, so what is a signature? A signature is something that in Bitcoin authorizes the spend of a coin, such that the person who received the Bitcoin can spend the coin and no one else. And this idea that no one else can spend the coin, we call that unforgeability. So we say the signature scheme is not forgeable, and that means no one except the person with a secret key belonging to a public key can create a signature over a certain message. And in the case of Bitcoin, the message is usually some variant of a transaction hash.
Got it. So how has that maybe changed? We recently activated Taproot. There's a bunch of new, interesting signature interactivity stuff I'll like to get into eventually. But what's the difference between ECDSA and Schnorr? And can you briefly touch on, anyone here, can you briefly touch on the discrete log problem?
Let me do that. Go, I'll take that. So as part of the new Taproot upgrade to Bitcoin, we have a new signature algorithm called Schnorr. The previous algorithm that was used in Bitcoin was called ECDSA. And so as Jonas just said, right, the point of a signature algorithm, you take the message, which is your transaction, you mix it up somehow with secret data in a way that anyone can verify, and the idea is that you have this unforgeability property. So only the person who has access to the secret data is able to sign the transaction. And if any part of the transaction changes, the signature is no longer valid, right? And the specific way that that's done is by an algorithm called ECDSA, which uses a whole bunch of crazy moon math involving elliptic curves and complicated algorithms and stuff. And in the Taproot upgrade, we have replaced ECDSA for Taproot outputs with Schnorr. And the difference between the two is actually fairly subtle. They both use elliptic curves. They both use a sort of linear-ish equation. They both have a very simple algebraic expression, which if we were doing a math talk, I could write them both on the board, and you'd almost wonder what the difference was. And the difference ultimately comes down to history, I'd say, which is that back in 1989 or so, when EC Schnorr was first developed by Klaus Schnorr, who is still a professor in Germany, by the way, he developed this signature scheme. He put a number of patents on it. 1, that was the number. And he then tried to collect royalties on the signature scheme. And because it wasn't widely used anywhere, it got no use, right? Nobody wants to start using a cryptographic scheme that you have to pay to use, basically. And that's always been true, pretty much for the history of modern cryptography. So nobody used this. So then a few folks at NIST, in particular Neil Koblitz, I think, developed ECDSA, where they took the Schnorr signature algorithm, they rearranged it a little bit, and they made it just different enough that it no longer violated the patents. And so this then became a standard, both because there was a big standards body behind it, and also because it was patent-free. And that was kind of the design, right? It was supposed to have all the efficiency and security and all those good properties of Schnorr, but not be encumbered by this patent. But as it happened, well, in practice, that is true. In practice, it accomplished all of those things. But Schnorr's system, by being kind of designed with cryptographic goals in mind, is a fair bit more elegant. It has a security proof in a theoretical model, which is much more plausibly related to real life. It also has a bunch of algebraic simplicity, and that's the big thing that I think we'll get into a bit later, that makes it possible to do all sorts of cool advanced tricks like multi-signatures and threshold signatures and adapter signatures and all these different new signature types. You can build those on top of Schnorr, and it wasn't really practical to build them on top of ECDSA.
So what is the difference between multi-signature and threshold signature?
Yeah, so kind of what was alluded to is one of the things that is much simpler to do now that we're using Schnorr instead of ECDSA is that you can have, so I think most people who use Bitcoin are used to having like a public key, and that's like an address. It's where your funds are stored. And then your private key is like the secret you know that then you can generate a digital signature in order to spend those funds from that address. And now you can kind of have shared ownership of a single pub key. Most Bitcoiners are, or well, some Bitcoiners are probably aware that you can have shared ownership using a Bitcoin script. It's usually called multisig. And that's kind of enabled by just putting multiple public keys on chain. But what these kind of new protocols enable is a way for multiple people to share just one public key that kind of represents all of them. But everyone who isn't involved doesn't need to know that it's multiple people. It just looks like a normal public key. And then multi-signature is when you have, say, like 2 people, and both of them need to kind of work together in order to generate just one signature for their one key. And then threshold, as the name suggests, would be something more like you have 3 people, but only 2 of them are needed in order to generate.
So it's like a subset of the parties involved in making that.
Yeah, so in some sense, threshold is kind of this general thing, and multi-signatures are just the special case where everyone needs to sign, which is kind of confusing because object multisig, like the way that we previously had of doing multisig on Bitcoin, or what's called multisig, is actually a threshold signature. But yes.
So I think it's a different state of mind now to perceive like the change from like a multi-signature to now what's more like an interactive aggregate signature. Can we briefly expand on how it works, the combination process, like what are these rounds I hear of?
So right now in Bitcoin, if you want to create a multi-signature, you use a check multisig opcode, or in the Taproot world, how it's called, check sig add. And the way that you are able to spend a coin is that you need to, so everyone who is involved in that setup needs to agree on a message, which would be some kind of transaction in our case. And then they just sign with their secret key and send the signature to some person that will aggregate the signatures and then broadcast the transaction to the Bitcoin network, for example. Now, if we want to use the tricks that Nadav mentioned, doing a real multi-signature where even though it's multiple people, there is only one public key involved and there's only one signature, the setup becomes a bit more complicated because now we call this signing process interactive because there are now multiple rounds involved, which means that the potential signers first send some data around, then they receive the message, and then they sign, and this way we have like a 2-step process, you could say, in order to create a multi-signature.
So are there some challenges, I guess, like if I had like a key in a safe, or do they need to all be online, like in certain instances? Like how does this like look for like the average person?
Yeah, there are some challenges definitely, which is why when designing these things, we try to remove these challenges as much as possible, but unfortunately they cannot be removed entirely in our universe, in our laws of nature, as far as we know. So just yesterday, we published a Bitcoin improvement proposal draft on the Bitcoin mailing list that contains a standard for how to create these multi-signatures. It's a 2-round variant as kind of the state-of-the-art research that we did. Previously, it was 3 rounds, and it tries to explain all the different footguns. There aren't that many, but you still need to understand, if you want to implement this, I'm not talking about users or anything, I'm talking about implementers of this specification. There are a few things that you need to be absolutely aware of. You need to read certain parts of this Bitcoin improvement proposal. I think if you boil it down, it's just 2 or 3 things. But if you follow them, you will be able to create a Schnorr signature, so a signature for a transaction that spends a taproot output.
Got it, got it. So what are some attacks? You know, I hear this thing called rogue key attack or some guy named Wagner. Like, what is?
All right. Yeah. Do you want to take this?
Yeah, I'll take the rogue key one, and then I'm gonna make you talk about Wagner. That's a hard one to explain. So the way that these signature schemes work, both ECDSA and Schnorr, is that you have this, what's called a linear equation, where you have some secret data, you have a message digest, you have basically an ephemeral key that we call a nonce. You put them together into a simple equation, you add all the pieces together, and you're off to the races. And when I say add there, I mean like something a little more technical than familiar addition, but still it behaves algebraically in the same way, right? If you add 3 things together, it doesn't matter what order you put them in, you can rearrange them, all that good stuff. So what a rogue key attack is when you take one of these multi-signature schemes that Nadav and Jonas was talking about, where you combine 3 keys from 3 different parties, say, however many you want. Let's say you have 3 parties, they all combine their keys into 1. So the goal is you have 1 key, 1 signature, but you have 3 people behind it, right? And the goal, of course, is that you want the 1 key to actually represent the 3 people, right? Like, certainly they should believe that, but also it should be a true belief. So what you can do during setup, if you're participating in this, say that we wanted to do like Vivek and me and Jonas. We're all doing one of these setups. So the idea is that we would each throw a key in the pot, we would add them all together, and then we'd have our combined key. And then later when we're signing, we would each do a signature, we'd add the signatures together, and then we get a single signature. And we actually have to do that in 2 stages, right? We throw some nonces in the pot, add them up, we throw some signatures in the pot, add them up. Everything's great. The rogue key attack is where what I can do instead is I can wait for both Vivek and Jonas to give me their keys. And then what I do is I make a key, and then I subtract their keys from my key, and then I put that in the pot. And so if you've been following everything, what gets mixed together is my key minus Jonas plus Jonas, minus Vivek plus Vivek, and what's left is just me. And so all three of us contributed something, and we added up something from all 3 of us, but I kind of ginned things up so that everyone else's contributions would be canceled out. And now, if I want to go move the coins without consent from either of them, I can go ahead and do that, because ultimately the final key is just me. So that's a rogue key attack. And the way to avoid it is to do what's called re-randomization, where when we mix the keys together, we need to rather than directly adding them, we need to first multiply them by a random factor, and you have to choose that random factor in a way that whenever I try to change what my contribution is, it changes the random factors for every other party. So I can't wait for everyone else to do stuff and then contribute my thing. We have to mix. We have to mix contributions from everybody. And so if I try to gin things up, my act of ginning it up will change the randomizers and thereby undermine my gin. So that's the rogue key attack. So that's one thing that we've had to address as we've developed these multi-signature schemes. Wagner.
Okay. Perhaps just to be clear, these attacks, they don't apply to the BIP that were proposed yesterday. We're talking about this, I think, because these kinds of schemes, they have a history, and these attacks were discovered on the way to the standardization of these schemes. One of these attacks would be a rogue key attack, but there are also other attacks. Perhaps you are aware that given some byte string and a hash function, let's say SHA-256, it's very hard to find a pre-image or an input to that hash function that hashes to a specific output. That is hard. However, what not many people are aware of is that if you have a sum of multiple hashes that should sum into a value, a specific value, then finding the pre-image for that sum of hashes is actually not that hard. And in order to find these inputs to the hash functions, you can use Wagner's algorithm, but there are also more efficient algorithms out that have just been discovered last year. But this attack actually appears quite often in crypto systems that we are interested in the Bitcoin world.
So I'm not sure if this is going to be helpful. This is a very technical thing. But one example of where that would appear is when you're trying to do a multi-signature, what you're combining is a linear combination, of course, of secret data, but also the hashes of the transactions. So if you can find a number of transactions whose hashes all add up to the hash of another target transaction, you can potentially get signatures on a bunch of good transactions where the good ones were chosen such that those signatures could be added up to get a signature on a bad one. And so that is, actually connecting this to a real system gets pretty hairy and technical, but because of this linearity property that I haven't defined, but I'm going to keep coming back to over and over, you can use this very abstract sounding Wagner attack and actually produce forged signatures using it in some some previous iterations of this kind of research.
So now that state-of-art research is out, what are some efficiencies gained? Like, I like to sync my full node and really brag about it. Is it faster now? Like, what's going on?
So it won't change past transactions, obviously. So the kind of current sync time isn't all that affected by Taproot. But new transactions, if people are using Taproot, are going to, Schnorr itself is just faster to verify already on its own by a little bit. But then with kind of the new standardization process, you can also now kind of aggregate a bunch of signatures that you want to verify together in a way that then you can verify them all at once in a way that's faster than verifying each signature individually. And that'll lead to, it will mean that as opposed to the universe in which we didn't implement Schnorr, we're faster than that universe in syncing.
So I can essentially verify maybe one signature for a whole block or one signature for entire 15 multi-sig, something like that?
Well, all of them do have to be Schnorr signatures. So people who are still using ECDSA, you still have to verify each of those individually. But I believe, and I guess correct me if I'm wrong, that you can kind of just batch in as many of these Schnorr signatures that are using the same standard together and kind of get benefits that grow with the number of signatures that you're verifying at once.
So there are two pieces to that, just to clarify. So one is this notion of batch verification, where if you have a whole pile of signatures in a block, and they're all Schnorr signatures, you can verify that much faster than just verifying each one in a row. And if you've got 3 or 4 of these, you can probably verify it twice as fast, but if you've got 1,000 of them, you could potentially verify it something like 8 or 10 times as fast. It's not a simple curve. I can just give you a multiplier, but it gets better the bigger your batch is. The other cool thing, though, that we'll see with Schnorr signatures is this, because we can do this multi-sig kind of constructions, oftentimes you won't even have so many signatures to verify. And I think that's probably in practice where we're going to see the bulk of the savings is in the signatures that aren't even on the blockchain because they no longer need to be.
Yeah.
I think one of the more immediate applications of this multi-signature technology is opening and closing Lightning channels, because there you are already in the setting where you have a 2 of 2, and the Lightning network already is a very interactive and stateful process, very different to hardware wallet signing in your using your bank vault or whatever. And this would, I think, benefit Lightning quite a bit, because right now you need to write 2 public keys to the chain as well as 2 signatures when you want to close a Lightning channel. And with multi-signature schemes, you can reduce that to 1 public key, 1 signature, which would make it cheaper to use Lightning.
Are there any other cool applications with these? I know Nadav works on DLCs. I know like there's also a pre-image or hash reuse along the path. What's possible now?
Yeah, so one really exciting application that is made much easier by Schnorr signatures is a variant that I believe Andrew came up with called adapter signatures.
Oh, yes.
And they kind of allow you to, say, bake in some more logic into your signatures than just kind of saying, like, yes, this person can spend this. You can kind of make it a bit more complicated. So essentially, what DLCs do is we utilize adapter signatures in order to make Bitcoin payments that pay different amounts depending on what, say, an oracle says happened in the real world. So say, like, if someone won an election or something like this, then there might have been multiple candidates. People can put money into a Bitcoin address that will pay to a different person depending on who wins that election, or all sorts of variants on this kind of thing. And I believe this also affects Lightning. You can essentially perform Lightning routing in a much better way than previously, or than it currently is done, using these adapter signatures. And one of the main benefits of this is that you don't have to use Bitcoin's native scripting language. You kind of bake it all into the math of the signature itself, and it all kind of just looks like normal signature activity on-chain, but it kind of makes it so that only the people who need to know kind of do the math and do all of the contract logic and everything else. Really, you only use the Bitcoin blockchain for the actual transfer of funds, which is what it's best at.
Yeah. So one thing that we've been dancing around through a lot of this conversation is that there's not just a scalability benefit here, that there's a privacy benefit as well. So one place that the privacy comes from is just from using multisigs directly. That already gives you a privacy benefit if you've got one key that potentially represents multiple people and potentially represents some complicated policy where it could be a threshold or some other arbitrary set of signers. In the Lightning case, things get a lot more interesting because, as you say, with these adapter signature constructions, you're able to start embedding some kind of non-trivial logic into the signatures themselves. And adapter signatures themselves, what they are, one way to think of them is a form of verifiable encryption. And what I mean by that is that I can take a signature, I can encrypt it in some way where I can prove that the data that I'm encrypting satisfies some algebraic properties that let me hook it into some other crypto system somewhere or something. So ordinarily, the point of encryption, right, is that you basically completely scramble your data. And if you, the idea is that the intended recipient can decrypt it and get the data out. But until they do the decryption, if they don't have a decryption key, there's nothing they can, like, they can't even tell that it is encrypted data, right? It could just be noise. With verifiable encryption, you can, provide some more substance to that. So in particular, when you are using the Lightning Network, the way that your payment channels work is, well, the way that Lightning works is you're actually chaining multiple payment channels off of each other, and you have these paths through the Lightning Network, and you're routing money through all this. And along a certain path, you have to maintain this kind of fixed identifier. I think it's an invoice ID or something in the UX. But what it is in the current Lightning invocation is it's some hash, it's some random hash of some data. And this hash is put into the scripts in all the payment channels, and it has to be the same, and that's how the payment channels are linked. The idea is that when you update one payment channel, it causes a pre-image of that hash to be revealed, and the revelation can then be used in the previous payment channel, which then, and every one before that. With adapter signatures, rather than using script to require that your signature has to come along with revealing this hash pre-image, right, you can use this form of verifiable encryption. You can say, by signing, you can say, my signature itself is an encryption key, or a decryption key, more importantly, it's both. So by signing this update to this payment channel, I am now revealing a decryption key in the form of the signature, and that decryption key can be used to reveal some secret data, which I can then take and use in the previous payment channel and chain it forward. And even cooler is that you can actually re-randomize that at each step. So now, rather than having a whole path where you have the same random ID in each one that somebody who had a God's eye view of the network could tell that it was all one path, you now have this re-randomization where even the people in the path itself might not know where it starts and where it ends because there's re-randomization happening at the hop after them and the hop before them. So there's a privacy benefit there, even within the Lightning Network. So it's
Interesting.
pretty cool.
So we have about 15 minutes left, and I'd definitely like to discuss scriptless scripts, Musig DN, or perhaps even CISA. And then there was a recent paper put out, and also some libraries from Jesse Posner regarding a threshold scheme called Frost. So let's try to rush through this.
Well, scriptless scripts generally refers to the use of adapter signatures,
Right.
so I think we've covered
Yep.
that one.
I think so. Well, I have one more minute.
Okay, yeah,
Let
go
me-
for
I'll
it.
be quick, though, I promise. Yeah. I was that on another panel a couple weeks ago, and I gave a 28-minute answer to the question, how long have you been writing software? So, but I'll try not to do that. I'm sorry, I'm doing it now. To finish my spiel about adapter signatures. So adapter signatures give you this kind of this verifiable encryption property, which you can use in the Lightning Network just to feed data through there. But what you can also do is encrypt other signatures, for example. So you can do arbitrary forms of atomic swaps and stuff where you have, say, 2 transactions on 2 different blockchains, for example, and you want to swap, right? You're trying to trade some Bitcoin for something worthless, right? And the worthless thing has its own chain, right? That they do, usually. And so you want to do this swap fairly, right? You don't want one person to give their money away and then the others just take it and then walk away. So the way that you do this is you set things up so that when the first person signs to take their money, that signature then decrypts a signature that gives the other asset away on the other side. So you get this atomicity in that form. Another more general application of this would be something called a zero-knowledge contingent payment, ZKCP, thank you, where what you are encrypting, rather than being another signature or something, is basically some arbitrary piece of data, and you provide this extra object called a zero-knowledge proof. And a zero-knowledge proof is a very general, very powerful cryptographic object, they're very slow to create. They have weird security models. There's lots of questionable things about zero-knowledge proofs. But the cool thing here is we don't put them on the blockchain, and we don't need them for long. They're kind of an ephemeral thing here. So what I could do is, supposing, say, that try to come up with a non-contrived example, right? I have some satellite imagery, okay, and I claim that I found some oil deposits, okay, and I'm trying to sell those to Chevron. And I don't want to just give them the satellite images, because then they'll take it and run away. And for some reason, they're really into high-tech, bleeding-edge cryptography and want to play games with me, even though that's really not what they do. And so what I can do is I can take this satellite image, I can somehow describe the evidence of oil in a verifiable, computationally verifiable way, and produce a zero-knowledge proof. Well, I'll take the image, I'll encrypt it. I'll produce a zero-knowledge proof that what I encrypted is a satellite image which satisfies these criteria, which Chevron agrees actually indicates evidence of oil. And now we do a zero-knowledge contingent payment, where the two of us jointly create a transaction where, in order for them to take my money, I have to sign a transaction, and my signing of that transaction, well, I know it's going to give me the money because that's the transaction that gives me money. My signing will then decrypt the image, which Chevron knows will be what they expect. And so we can execute a transaction that way, even if the two of us don't really trust each other. And even if nobody should trust either of us, the zero-knowledge proof will step in there. So this general framework of playing games like this with adapter signatures is what we call scriptless scripts. So.
Got it. So we're going to take a step back, actually. No more Musig DN. I think we got our ZKP crypto catnip out of the way. Let's take a bit more applicable thing. I know you and Tim Ruffing also work on half-ag, Musig 2. What are these advantages and efficiencies potentially gained for things like lightning gossip? Can you touch on this?
From aggregation, you mean? Okay. I think it would make first sense to distinguish what we call signature aggregation from multi-signatures or threshold signatures. And for us, the main distinction is that in multi-signatures or threshold signatures, you only have a single message. In the Bitcoin use case, that is dependent on the input that you're spending, or dependent on the coin that you're spending, which means you have some set of people, and they have shared ownership over a single coin. Now, when we go to the signature aggregation world, there are multiple signers, and each with different messages, right? So this corresponds to a transaction with multiple inputs, and this transaction must have multiple signatures, and each signature will be over a different message because the signature is used to authorize the spend of a different coin. So we call these schemes signature aggregation. What they are doing is they really aggregate signatures, and this doesn't have privacy benefits, in general at least, but it has scalability benefits because a big part of transactions right now are actually signatures. So we could try to aggregate these signatures into a smaller signature. And there we again basically distinguish two different types of schemes, mainly half aggregation and full aggregation. And full aggregation is a bit simpler to explain because that works by, or the output of the full signature aggregation algorithm is a single signature. So in an ideal world, every Bitcoin transaction would have a single signature. Unlike today, where there's a signature for every input, basically. But creating these signatures has similar interactivity properties than multi-signatures. So it's not so easy to do, and how to exactly do that is still an open research problem. For half aggregation, we don't get the benefits of having only a single signature in the end. We basically are only able to aggregate half of the original signatures together, but this process is non-interactive, so anyone can do that. And that would be something that could be added to Bitcoin consensus, perhaps, at some point in the future, but it may have also implications on protocols on top of the Bitcoin network, such as Lightning, because Lightning, at least right now, gossips a lot of signatures around to prove that nodes actually have open channels. And these signatures are just bare single signatures. So what could happen is that instead of each sending a single signature in order to do a single proof that a channel exists, some party, could be anyone, could just aggregate these signatures into a single half-aggregated signature then in order to reduce the size of the messages that need to be sent around in the Lightning Network.
Fascinating. Hopefully we'll get that sooner than later. All right, Nadav, what is Frost?
Well, Frost is a specific proposal for threshold signatures on top of Schnorr. I believe it stands for flexible around optimized, what's the S?
Signing signatures.
Something threshold. Oh, Schnorr threshold
Schnorr,
signatures. There we go. Yeah, so essentially, it is so it's a two-round proposal, meaning that well, I guess there's a pre-computation you can do so that it kind of looks like there's only a single round, where that kind of looks like normal signing, where you just do something once, like everyone generates their part of the signature, and then someone puts it all together. But really, there's also kind of like a setup round. So there's a setup round and then a signing round is maybe a high-level way to think about it. Essentially, what you do is everyone kind of has their own private key, is how you could think of it, or secret share. And then together, they have one private key. It's not as simple as just adding all of those keys in a pot, but you do a little bit more math, and you end up getting a key which then could, in theory, be derived by any, say, 2 of 3 participants, or 3 of 5, or T of n. But then rather than actually doing that, because you don't want people to just know what this private key is, because then they can sign for the group, so what you do instead is you collaboratively, any 2 of 3, or 3 of 5, or whatever threshold you want, of all of the people can get together and collaboratively generate each person generates a partial signature using their own secret share, and then it's all put together, and if you have at least T people, at least 3 of the 5 people, for example, then you generate just one normal-looking Schnorr signature for the one kind of group key. And it's kind of done in a simple enough way that it works well with a lot of other things that you might want to do. Actually, I don't know if it works with adapter signatures. I imagine that you would be able to hack that together if you wanted, or similar approaches could.
Adaptive signatures mostly only work with 2 of 2 setups, so
I see.
there's not room to do a threshold in
Right.
2 of 2.
Right. Okay, yeah. Well, it kind of is similar in nature to how multi-signatures look, but it's done more generally. And I guess if Jonas wants to talk about the trade-offs between using something like Musig and Proc.
We can have a bonus round about blind signatures or ring
Or
signatures
that.
if you'd like to.
I think one thing that's also interesting to get across is what are the different stages that these proposals are right now, because people in the audience might be interested to use this eventually. Mm-hmm. And so what we're mostly talking about right now is only the lowest level that you're really interested in, which is the cryptography part, right? But there are more parts before you can actually use this in your wallet, right? There needs to be standardization first of the crypto scheme. And for multi-signatures, we are, as I said, we published a standard yesterday. For Frost, I would say there it's a bit more early, but there are also standards progressing that will be eventually usable with Taproot and tweaking and whatnot. But then there is also the other layer of how does this integrate with wallets, really, that you can have multiple wallets independently implemented from different vendors that work together and create such a signature. And that is, I think, a really interesting thing in the future, how to exactly do that. That might be more difficult for some schemes than for others, right? For multi-signature, which is a more specific scheme, N of N, that might be a little bit more, a little bit easier to do for wallet implementers than something, for example, like Frost. And you asked about blind signatures?
Blind and ring, whatever you think we can kill a minute 30 with.
Okay.
I say ring. Do ring.
I'd say blind signatures.
Let's do it.
Yes, blind.
Okay, so what blind signatures are, they are basically a client and a server protocol where the server signs some message that came from the client without knowing what this message is. And also such that the signature won't be correlated with the message in the future or even the signature in the future. And how is this used? This can be used, for example, for federated eCash or eCash in general, which is, I think, one of the interesting direction that the Bitcoin community is looking into, where you have much better privacy guarantees than anything you could achieve with blockchains or Bitcoin in particular, but you have other trade-offs. And these blind signature schemes, they don't need to be part of Bitcoin consensus, which means that we can use more exotic schemes that don't have the trade-offs of interactivity that we discussed with multi-signatures or complicated setup like in threshold signatures, but we can have more exotic cryptographic assumptions and then have a scheme that is simpler to implement and harder to mess up. And also that has properties like threshold blind signing, where you have a whole federation that would require a signature on a token or whatever. Yeah, so that's I think the way how you could use blind signatures in Bitcoin.
And this is essentially mini mint or similar applications.
Yep, exactly.
That is.
Well, I guess that's pretty much it. I'd like to conclude this panel. Let's get a huge round of applause for Andrew Polstra, Jonas Nick, and Nadav Cohen.